discussing how integer arithmetic is performed in a computer. We have seen how addition, subtraction, and multiplication is done. Today, we shall discuss how division can be done. In the case of a multiplication, we use the basic technique of shift and add. In the case of a division, we will be using the basic technique of shift and subtract the way that we learned doing the division from the primary school days. Let us take an example and see how the division will be done. But first, let us see that what hardware will be used. The same basic hardware that was used for multiplication will also be used for division. Here there is an M register, there is an A register and the Q register which are connected. In the case of a multiplication, we had been using shift right. Here we will be using shift left, the green line. This Q minus 1 will not be used, and what emerges out of the most significant bit of the A register may be shifted to the C. That carry flag, we call it a carry flag. The divisor will be kept in the M register and the dividend will be kept in the Q register. The A register will be cleared. Now, this is the unit which will be doing addition or subtraction as is necessary, and this is the unit which will do that instead of add, subtract and shift control. Let us first see the algorithm that we will be using. We start by initializing this. The A register is cleared. As I said, the divisor will be put to M register, dividend will be put to Q register, and the number of bits that will be put into the count N. Now, we will first discuss about division of unsigned numbers. When I say unsigned numbers, that can be used also for sign magnitude representation. In that case, in the case of a sign magnitude representation, we will have to first strip off the sign bits, make them unsigned numbers, do the division, and then properly assign the sign bit to the result, that means the quotient as well as to the remainder. Now, let's come to that algorithm now. After this initialization is over, we come over, we shift left the A register and the Q register together and then do this operation, that means subtract M from A, and the result is put into the A register. Now we check the result. If we find that the result is less than 0, in that case, naturally that subtraction is unsuccessful, and as we know that A register has to be restored. That means we will have to add M to A register to bring back the value of the A register to its original one. And since this subtraction has failed, 0 will go to the Q register. But if this subtraction is successful, that means A is not less than 0, then the Q0 bit will be made 1, telling that the subtraction has been successful. We come over here, N is decremented, and if N is non-zero, then we do this operation once more. This we continue till we find that N equal to 0, which means the entire operation is over and we come to the stop. Now let us take an example and see that how this works. Let us say that the divisor, we are trying to do the division of 7 divided by 2 as an example. Now, divisor is 2 and that has been put into that M register, that means here. Dividend is 7, that will be kept in that Q register, and the A register is clear. The A register is clear, and our operation starts from here. That count 3, since this is 3-bit number, count 3 has been put to N. Now, let us go step by step with this operation. Next is that we shift left one bit position, that means 0 comes here, this 0 comes here, this 1 comes here, this 1 comes here, and this 1 comes here, and we will have to decide what will be the Q0 bit. Now, next operation is that we subtract A minus M goes to A. Now, A is this, okay, A is this value minus M if we do, that means 0, 0, 1 minus if we do 0, 1, 0, the result obviously will be negative, and therefore, we restore the value of A, that means we keep the value 0, 0, 1, and 0 is pushed into the Q0 position. You see 0 has been put into the Q0 position. Count is reduced to 2. Next come, once more we make a shift left, that means this 0 comes here, this one comes here, this one comes here, and so on. This bit has to be decided, and once more we do the operation of A minus M. You see, now if we do that A minus M, the result is greater than 0, and therefore Q0 comes as 1 here, and count is reduced to 1. Now we shift left once more, this A and Q register, this bit is to be decided. We subtract once more A minus M and see that Q0 equal to 1, since the result is greater than 0, that means the subtraction is successful. Therefore, we put Q0 to 1, A now is reduced to 0, which means we stop the operation now. This contains the remainder, and this now contains the quotient. That means the Q register will be containing the quotient, and the A register will contain the remainder. You see, if I divide 7 by 2, we are supposed to get 3 as quotient and 1 as remainder, which we have obtained. Now, this is essentially division by unsigned numbers. Now, let us see that in the case of that signed numbers, what we can do. As we say that the signed numbers, we will be considering the 2's complement representation. The case of that sign magnitude representation can be treated with by the help of the algorithm that has been done for that unsigned numbers, okay, by stripping off the sign bits and taking care of the sign later on. Now, in the case of an unsigned numbers, this is the algorithm that we will be using. First step is once more that divisor is put to M and AQ is loaded with the dividend. Now, here that when we load the AQ, as we said in the case of a multiplication also, the sign bit that comes in the Q register is propagated into the A register. Therefore, we propagate the sign bit towards the left, okay. Then count is set to the number of bits. We have given the algorithm in stepwise. Then in step 2, we shift left A and Q together. Now, if we find that if M and A are of the same sign, then we subtract. Otherwise, we add. This is our step 3. The step 4 is, if operation at step 3 is successful, we set Q0 to 1, else we set Q0 to 0 and restore A. Here, if the operation is unsuccessful, we restore A. Once we decrement N, and if we find that if non-zero, we go to step 2. That means we start this loop once more, starting from step 2. That means we shift left, then check the sign of M and A. If the same sign, we subtract. If they are not, we add. and if the operation at step 3 is successful, we put 1 to Q0, else we put 0 to Q0 and restore A. This continues till we find that n equal to 0, then we stop it. We'll find the remainder will be in A and the quotient will be in Q. But the quotient will be this, that if the divisor and the dividend are of the same sign, then the quotient will be as it is in Q. Else, to get the correct quotient, we'll have to take the 2's complement of Q. Now, for this part, we'll see once more. Let us take an example that of doing division by 2's complement numbers. Say this is what is the operation that we would like to do, that we take minus 7 and try to divide by 2. Now, the divisor is 2, that is a positive number, therefore, it is 0, 0, 1, 0. The dividend is minus 7, it's a negative number represented in 2's complement form, that will be 1, 0, 0, 1, that is pushed into Q, and the sign bit has been propagated into the A bits, A register. Now, it's a 4-bit number, we set the count to be 4. Okay. Now, let us go step by step as per the algorithm. Up to this is our initialization. Let us come over to this step. Okay. We shift left A and Q as per our procedure. Therefore, we get this value. Okay. 1 comes over to here. All these ones are shifted out. 1 is shifted out of this into the carry, but we don't consider the carry here. This 0 comes here, this 0 comes here, and this 1 comes here. We'll have to decide about the Q0 bit. Now, A and M are opposite sign, okay, and therefore we do the operation A plus M. Now, as soon as we do that operation A plus M, let's see what happens. It says A is 1, 1, 1, 1, and M contains 0, 0, 1, 0, and if we add, you see that it will be 1, 0, 0, 0. The operation is unsuccessful because the sign of the A register changes. Okay. As soon as the sign of the A register changes, we know that that operation is unsuccessful, and therefore we restore the value of A. That means 1, 1, 1, 1 is put back into the A register by adding, by putting back the values of the A register, original values into the A register. Okay. And we put 0 into Q0 here, and N is reduced to 3. Okay. Now, once more we shift left A and Q. If we shift left, we get this. Q0 has to be decided now. Once more we do A equal to A plus M, and we find that it is unsuccessful once more. That means, say, now it is 1, 1, 1, 0. We add 0, 0, 1, 0, and we get once more that the sign bit of the A register changes, telling me that the operation is unsuccessful. We restore the original value of A here. Q0 is put to 0. Q0 is put to 0, and count is reduced to 2. Count is reduced to 2 here. Now, we shift left once more, make A equal to A plus M. Now, this time it is successful because you see it was now, say, 1, 1, 0, 0. We add 0, 0, 1, 0. We get 1, 1, 1, 0. The original sign bit and this sign bit is the same, and therefore the operation is taken to be successful. Q0 is put to 1, and count is reduced to 1. Now, we shift left A and Q once more. We do A plus M. It is successful. Therefore, Q0 is set to 1, N is 0, and we come to a stop. Now, let us see the result. the result is that remainder is 2's complement number and represents minus 1, okay, which is actually the remainder of minus 7 divided by 2. Now, let us see the quotient. The quotient, as we said in step 6, that we said that the remainder will be in A. If the divisor and dividend are of the same sign, then the quotient is in Q, else the correct quotient is obtained by taking 2's complement of Q. Okay. Now, here A and M are of opposite sign, and therefore, to get the correct quotient, we will have to take the 2's complement of this number, and if we get the 2's complements of this number, basically it is minus 3. Therefore, my remainder is minus 1, quotient is minus 3, and you see that now fits into this equation, that if the dividend should be obtained as quotient into divisor plus remainder. The dividend was minus 7, the quotient is minus 3, and divisor is 2, and the remainder is minus 1, and therefore, our result is correct as per the algorithm that we have followed. Okay. Therefore, this is a simple algorithm for division that we can utilize using 2's complement representation of integers. Now, I would like to stop here regarding that arithmetic operations of integers. Let us see at this point summarize that what we have discussed. So, as integers are concerned, we have discussed the sign magnitude as well as the 2's complement representation. The sign magnitude representation and later on the algorithms that we have given for addition, subtraction, multiplication, and division using unsigned numbers are mostly of academic interest, basically because these are not used in computers. The representation that is almost universally used are 2's complement representation. Now, the 2's complement representation algorithms that we have given are simple in nature. Many fast algorithms and better algorithms have come up to this operation much faster. Any standard textbooks on computer arithmetics can be consulted to learn more about these arithmetic operations. Our purpose here had been to give you a simple circuit as well as some simple algorithms to show you how in 2's complement representation these arithmetic operations can be performed. Now, one thing that I should mention here, that the representation that we are taking here, that means that say 2's complement representation, say any number that we take a 4-bit number 1110, say this number a 4-bit 2's complement number I have taken. We call it a fixed point representation. We call it a fixed point representation because we assume as if the binary point is at this, to the right of the least significant bit. We do not represent the binary point. We say this is a fixed point representation of an integer. Similarly, if a positive number say 0101 is fixed point in the sense that we assume the binary point is at the right hand side of the least significant bit, which we do not consider. Now, this we use to represent integers. What we should do to represent floating point numbers will come to in the next portion of our lecture. But before that, one important issue we should discuss, and that is, say for example, we are doing operations. Now, what happens if we find that the operation, after operation, the result is such that it overflows the registers? That means the register cannot contain the result. Now, to tackle this situation, what are done is, and to tackle some other situations, okay, what are done is some flags are kept. Okay, we call them carry flag then overflow flag, then sign flag, and sometimes we call that parity flag. These flags, that means all of them are a single bit register, you can say. This is generally known as C. This we call as V, the overflow flag. This is the sign flag, and this is the parity flag. These are the abbreviations generally is used. This is carry, this is overflow, this is sign, and this is parity. Now let's see what are these. So far as the carry flag is concerned, we have shown over to here. That means anything that comes out of the most significant bit of this register comes into this. Similarly, while doing some arithmetic operation, if there is something that flows out of the most significant bit that is put into the carry flag, we call this a carry flag. Okay. Overflow flag I will come to. The sign flag essentially, as I said, that in the case of any representation, either sign magnitude or 2's complement, let us take 2's complement here, the first bit is a sign bit. Therefore, the first bit of any register, okay, this one is a sign bit, and if the result is here, this sign bit is taken to be the sign flag. And parity is, say for example, if a 4-bit number we take, say 1, 0, 1, 1, parity is a number of ones that we have in a representation. Here the number of 1 is 3, which is odd, then we say this is of odd parity. If the number is 0, 1, 1, 0, the number of ones is even, then we call it to be of even parity. Therefore, the parity bit tells us that what kind of parity the number consists of. Now, some computer keeps it as even parity. That means it puts 1 when the parity is even. Sometimes the other way it can also be done, that we put 0 when the parity is even, and when the parity is odd, we put 1, which means the parity bit says that what is the number of ones in a particular result. Okay. If we just detect even parity, then the parity bit will be 1 when the number of bits in the number is even, otherwise it will be 0. Now let us come to that overflow flag. Let us take few examples to show you that what the overflow flag does. Okay. Say we take a number, say plus 5, the number will be 0, 1, 0, 1, and say we want to add with plus 4, say 0, 1, 0, 0. You can see immediately that if we add, we get 0 here, we get 0 here, we get 1 here, right? Now, this definitely, if we are thinking in terms of 4-bit numbers and 2's complement, this is a wrong result, because that plus 9 that would have been the result, the correct result, cannot be contained in this 4-bit. Okay? Therefore, this is a wrong result. The situation is, just mark one thing, that in this case, a carry has emerged from here and has entered over to here, but there is no carry that comes out of the sign bit position, that means most significant bit position. Okay. Let us take another example. Say we take minus 5, which is 1, 0, 1, 1 in 2's complement. Say we want to add with, say, minus 4, that is 1, 1, 0, 0, and if we add now, we get the result 1, 1, 1. This turns out to be 0 and a 1 emerges out of the most significant bit. Okay. Once more you see the result is wrong, and if we observe here that we find that a carry has emerged out of the most significant bit. Therefore, this is wrong, this is also wrong, and one observation we do that in this case there is a carry from say n minus second bit to n minus 1th bit in an n bit representation. Okay. I mean n bit number, where the most significant bit is the n minus 1th bit and this is n minus 2 bit. Here there is a carry out of that n minus 1 bit. This is our n minus second bit. Okay. In both the cases, the answer is wrong. Now let us take cases where the answer is right. Say we take plus 5 and it's represented as 0, 1, 0, 1 and say plus 2, say 0, 0, 1, 0. Now if we add it, then we get that 1, 1, 1 and 0. You see there is neither a carry out of this position nor a carry out of this position, and we find that the result is correct. Similarly, let us take say minus 5 and say plus minus 1. Okay. This is 1, 0, 1, 1 is minus 5 in 2's complement, and minus 1 is 1, 1, 1, 1, and if we add them we get say 0, 1, 0, 1 and a carry comes out of it, this bit. Okay. Here we find that a carry has emerged out of this, also a carry has emerged out of the most significant bit. Here also the result is correct. Therefore, a simple rule we can devise that when the result will be correct, if there is no carry out of the n minus 1th bit, that means most significant bit, okay, and n minus 2 bit for an n bit number, where the first bit we call to be 0th bit and the most significant bit to be n minus 1 bit, okay, then we say the result is correct. Or if there is a carry out of the n minus second bit as well as the most significant bit, which is my n minus 1th bit, okay, if both carries are there, then also we call to be the result to be correct. But if there is only one carry, that means the carry from the most significant bit, which is our n minus 1th bit, or the carry from n minus second bit, there is only one carry, then we say the result to be wrong. Okay. Now, under that circumstance, these things can be captured and this thing can be captured by the hardware and we can set this overflow bit to be 1 or 0 accordingly. 1 means an overflow has taken place, okay, which means the result is wrong, and 0 means the overflow has not taken place, which means the result is correct. Okay. A simple, as we will find later on, a simple exclusive OR gate will do the job. Exclusive OR of this carry and this carry, okay, will do the job to detect the overflow. Now, that is all so far as our integer arithmetic is concerned. We will not dwell on integer arithmetic anymore. I suggest that you take some examples follow the algorithms that have been given to convince yourself that all the algorithms do work. Okay. Now, let us come to the next point. That means we have seen how integers are represented as a fixed point number. Let us see now how real numbers are represented. Okay. Say when you come to the real numbers, say we take a number say 0.0002357. Okay. Now, as we call it a scientific notation or a normalized notation, we put this dot, I mean we just shift out all the zeros, we put the dot over here, that's 0.23567 and say 10 to the power minus 3 because of this shift over here, this 10 to the power minus 3, we say this we call the normalized representation, where the significant digit after the dot is a non-zero digit. Okay. Now, it is quite okay, but say we do not have sufficient space to keep all the 4 digits here. In that case, naturally, we will have to get rid of this digit and we should keep it say 0.2356 into 10 to the power minus 3. Now, when we discard this digit, if we find, depending upon the rule that we follow, that if we find that say if it is more than 5, then we increment this by 1 to make it 7. We call it rounding off. Okay. This is what we call a normalized representation of a decimal number. Right. This is the normalized representation of a decimal number, we call it. Now, the sign may be either plus or the sign may be minus. Therefore, in the case of normalized representation, we can thought of this way, that as if there is, if you want to keep it, one position for the sign which is either plus or minus, then there will be few positions say for, we call it exponent, say minus 3 is the exponent here, right, and then there will be few positions say 2, 3, 5, 7 to keep what we call is the mantissa. This is our mantissa. This we call, as we know, that exponent, and this is the position for the sign. Okay. Whenever C is an exponent, in the case of a decimal number, it is 10 to the power the value that is here. Now, let us say another situation where the number is say 356.2345, and we want to represent in the scientific notation, as we call it, that means in the Mantis exponent form. We say the number is a negative number, then we will have to basically represent this one as minus in a normalized form 0.3569 and into 10 to the power, the thing is shifted over to here, therefore plus 4. Okay. And now, since we have only 4 positions for keeping the mantissa digits, the other digits from this has to be all rejected out. Therefore, in this form, our number will be minus, the exponent is plus 4 and the mantissa is 3569. Now, we know that the decimal number system that we use is a positional number system. In this form, whatever is after the decimal point, that has a weight we know of 10 to the power minus 1. This has a weight of 10 to the power minus 2. This has a weight of 10 to the power minus 3 and so on. Okay. The exponent, this can be either positive or negative. Naturally, the number also can be either positive or negative. Now, since computer represents numbers only in the binary form, let us see what happens in the case of a real number that we represent in the case of a computer. Here also, instead of a decimal point, we will have a binary point. For example, we will represent a number, say 110, say this binary point, say 011, will be represented as this, that this is has a weightage of 2 to the power 0, this has a weightage of 2 to the power 1, this has a weightage of 2 to the power 2, and anything that comes after the binary point will have a weightage of 2 to the power minus 1, this has a weightage of 2 to the power minus 2, and this has a weightage of 2 to the power minus 3. This is a binary number with a binary point. Now, if we want to normalize, represent it in a normalized form, then this binary point should be shifted over to here, and we have a representation of say point 1 1 0 0 1 1, and that will be multiplied by 2 to the power, since we have shifted to the left, plus 3, and this 3 will represent as 0 1 1. Okay. Now, once more, we are assumed that 6 significant binary points we can keep, and therefore, we can have a representation as that we keep first the, say this is a positive number, therefore, keep the sign bit, say 0 is the sign for this number which is positive. Then we keep our exponent bits, say 0 1 1, that this is a positive exponent. To represent that, we have this 0 bit over here, and then we have what we call is a mantissa bits, okay, that is 1 1 0 0 1 1, right. Let me see, this is our sign of the number, this is the exponent, okay, signed naturally, and this is our mantissa. We assume here, when we represent it this way, that as if the binary dot is here, but we do not keep any position to keep the binary dot. Any representation of the binary dot is not there, only is assumed that binary dot is here. For example, here also, in the case of it, when you putting that mantissa 2357 for the decimal representation, we assume that a decimal dot is here, but we do not represent it because we do not need to represent it. Now, this is the representation for a number which you can represent by with the help of a binary point. Okay. Now, such a number we call a floating point number, and which actually represents a real number in the computer. So, let us see what turns out to be the situation a bit clearly, that say we have a 32-bit representation, okay, we have to keep certain bits for keeping that exponent. Okay, we can here, for example, in a 32-bit representation, we have kept 8 bits for that exponent, then 23 bits for the mantissa. That mantissa sometimes is called also in some books you will find is called significand, that there is 23 bits we keep for the significand, 8 bits for that exponent and 1 sign bit. Whenever we set exponent, basically we mean that whatever we are representing, here it is 2 to the power that. Now, since we can have with 8 bits, we can represent numbers from minus 128 to plus 127. Essentially, therefore, we can represent numbers starting from 2 to the power minus 128 to 2 to the power plus 127 multiplied by whatever is the mantissa representing with a binary dot at this point, and the sign of the number is represented here. Okay. It's positive, then it is 0. If it is negative, that this is 1. Now, with this, let us see the range of numbers that we can represent. Okay. The range of numbers that we can represent with this representation is this. Say there is a 0. We say 0 to be when all exponent is 0 and all mantissa are 0. Okay. Then this is 0. Then from this point to this point, I mean this is the real line. From this point to this point is a positive numbers that we can represent. Okay. Now, the first positive number that we can represent is that there is a single dot here. Say here 1, then followed by all zeros in the mantissa bit. Okay, that is this number. That means this is point here, and that is this number is 0.5 to 2 to the power minus 128. Similarly, this number is 1 minus 2 to the power minus 23 bits, because this is of 23 bits. That is this number that we can represent on the positive side of it. Similarly, on the negative side of it, we can represent minus 0.5 into 2 to the power minus 128 to minus 1 minus 2 to the power minus 23 into 2 to the power 127. Therefore, this is the numbers, real numbers, some of which we can represent by this number representation scheme that we have said here. And on the negative side, these are some of the real numbers, that is some of the real numbers lies here, which can be represented by this number representation scheme that we have said over to here. And some numbers are there which cannot be represented at all. For example, here are the numbers which cannot be represented. Here are the numbers that are not represented. And as we will see that there are many numbers within these 2 points also, these 2 limits also, and these 2 limits also, which cannot be represented, the real numbers. This, in fact, we call the floating point representation, and we will elaborate more on this floating point representation and talk about the pitfalls of the floating point representation when we start our next lecture.